payoff. And E3 has another function, but it's relating to the demand process, but this is also going down with the idea that the ideal conditions will be when it becomes asymptotically small. Of course, different function, different schemes of acceptance might be worked out. It's not clear ultimately what would be the better. Now I have some more graphics to show. Should I escape here? Yes, and yes. Now this doesn't come out on the regular PowerPoint so well. By the way, I have also, the paper is printed. My paper recently appeared after, it was really more than 10 years of work. It was published in a journal called the International Game Theory Review, and they put it in a special issue. And that issue was nominally in December of 2008, but it actually appeared in late spring of this year. And that published for World Scientific. There's one thing about the way that's published. The published thing in the journal shows the graphics without color, but the data that had been sent into the journal had the graphics in color. However, the journal, how they operate so that on the email you can go to the journal and you can get a PDF of the whole paper, and in the PDF file, the graphics have regained their color. I guess something about the printing in the actual printed form, but they could provide it. Now this is where I have a. This is. I'm not seeing the mouse. Here it is. Now this chart, the assistants, it was an NSF project, National Science Foundation, and the assistants were students at Princeton, which were supported for doing some work by that. This is the chart that best reveals the comparison between these model results, and these are approximate because the epsilon quantities have not been reduced, in fact, to zero, but to small numbers. I'm not sure that it's very easily visible. Someone who doesn't have telescopic vision. But a quantity called B3 is varying. B3 represents the strength of players 1 and 2, what they could do without cooperating with player 3 at all. They just form a coalition. They either accept the other, and then player 3 is out of it. If this could be calculated up to the level of, they could have 70% of the payoff. They could get 7/10 of 1, and beyond that, I couldn't calculate it. Some problems appeared in the calculation, where the students were doing the multiple point. But this was calculated by a student named Ludmer, Sebastian Ludmer. This was actually done in 2004. It's a very nice chart. But the interesting thing is you can contrast it with another idea, which is a very popular and nice interpretation for cooperative games. It gives results which are nice in many cases, and it can be calculated with some difficulty for relatively large numbers of players, like maybe 15, but the effort goes up exponentially to get a complete calculation. It's the Shapley value. This was developed soon after the time when I was developing some ideas, my original ideas in game theory. Now, the Shapley value is this blue line. This is linear. The Shapley value has a linear property that can be used as an axiomatic description of it. It's a question of whether the values of cooperative games should depend linearly on the data that is available, including characteristic function numbers. If it should depend linearly, well, then that's it. The Shapley value is the only answer. This is our model. This starts out much smaller. Now, the other thing is something also popular, was developed in Israel, called the nucleolus. Another thing that's called the modified nucleolus was developed by Peter Sudhalter, who is a German, and he's now in Denmark, southern Denmark, I think. He's a known game theorist. But it's not quite the same as the nucleolus. Well, what happens here is, as long as B3 is not more than 1/3, the nucleolus says that all players should get the same. There is no imbalance of the payoffs. This imbalance thing is how much player 1 plus player 2 get compared with twice of what player 3 gets. If they all get the same, then that's 0, like here. Or also like here. The nucleolus says that if the coalition strength of player 1 and player 2 together is only 1/4, then they're not going to be able to use that. The players are all in practically the same situation. They could just get 1/3 each. But the model works out, it turns out in this case to be between these, up to here, but then it's lower than both of them. And ultimately, well, in this, player 1 and player 2 are not getting much. Now, if this could go on smoothly, it would turn up rather rapidly. But the game doesn't really work out like that, because some of the behavior describing quantities move to become 0, and they can't be allowed to become negative. So the equations would have to be changed to adjust for it in a proper way. But in this area of work, I'm still studying things. This has not been perfected, particularly because a set of 10 games were studied experimentally, and all but one of them had this problem of difficulty from computing it from this model point of view. Now, a similar calculation was made I didn't see the mouse. Let me, where is it? This one was worked out by a different project assistant. Here the asymmetry of the characteristic function connected with this game was that BZ was allowed to be different from 0. B3 was 0, which meant player 1 and player 2 could not benefit at all. But there was a standard amount which was called BZ, which would be both B1 and B2. This would correspond to the player 3 and player 1, that was B2, or player 3 and player 2, which was called B1, and they could benefit, but player 3 would be the key favored player. He could benefit on a 2-person reduction level with either player 1 or player 2. So how much can he benefit? Well, this is how much